In this video, I am reviewing some of the basic notation and ideas of classical mechanics, things that you may have learned in your physics course. The video kind of accompanies the document I posted on D2L entitled Equations of Classical Mechanics. So first of all, we'll introduce some notation. Particle moves, say, in one dimension. Its position is indicated by the variable that we call x. And as the particle is moving, we can define its velocity. Velocity, we can think of graphically, if this is x on this axis and time on this axis, the motion of the particle with time is some curve on this tx plot, and the velocity at this particular point is simply the slope of this, the slope, and that's indicated by the letter V. Okay, the slope indicates how fast position is changing with time. Mathematically, we write V equals dx dt, the derivative of x with respect to time. And in the notes, I have this notation, x with a dot above it. That is, I've been led to believe that you no longer use that notation. But back in my day, we did. A dot above a variable indicates its time derivative. Okay, continuing definitions, we also have acceleration. So acceleration is indicated by A. A is how fast velocity is changing with time. These are often velocity and acceleration are often confused. You should avoid that. But the derivative of velocity with respect to time is actually the second derivative of x with respect to time, indicated this way. Okay, some basic definitions. And then continuing the definitions and notation, if this particle can move in 3 dimensions, the position is actually indicated by a vector, which has 3 components. So the vector, I will use this notation. The vector position is r, and I will put a little arrow above. That'll be my notation for a quantity that is a vector with 3 components, and that's a shorthand notation for the triplet of numbers indicating the position, the x, y, and z components. Okay. Similarly, velocity. The velocity is also a vector consisting of the time derivatives of the x and y and z components separately. So vx, vy, vz. And similarly, acceleration is also a vector. Acceleration has 3 components, which I indicate a sub x, a sub y, a sub z. Okay. Now, with this introduction to notation, you should remember Newton's law. So particles, the motion of this particle depends on the forces acting on it, and so we simply write force equals mass times acceleration, or if we're in 3 dimensions, the force is again a vector with 3 components, and it's mass times, so same equation, just with vector notation. Okay, so we will do, I'll introduce a very simple example. I think you probably did a lot of problems like this in your physics course, and that concerns the motion of an object under the influence of gravity near the surface of the Earth. So that, so the particle can be above the surface of the Earth, and that would be indicated by the component in the z direction. The z is up and down, and the x and y component, x and y, would indicate position on the surface of the Earth. So now we'll assume that the force acting on the particle is strictly that due to gravity, and in a limited region near the surface of the Earth, the force is constant, and it's in the downward z direction, and so the force acting on any particle, excluding things like friction and all that, is this vector. There's no x component, no y component, 0, 0, and then minus mg. G is the acceleration due to gravity. Okay, so now this equation has many solutions. It kind of depends on where you start, like what initial velocity the particle has. So what I'm going to do here is just present one particular solution. We'll say the particle starts out moving in the x direction and in the z direction. So we'll say it has an initial velocity, which I'll indicate vx0. I'll give that a value. I'll say that's 5 meters per second. Okay, and it has an initial velocity in the z direction, vz0. We'll say it's moving upward at 10 meters per second. Okay, and in one of the problems I'm going to have you actually substitute in those numbers, but simply I'm not going to attempt to show you how you arrive at a solution. I will just state what is the solution. What is a solution based on these initial conditions? And I will assert that the solution to this, the solution is simply to find what is the position as a function of time. So I will assert that the solution R is a vector with these three components. The x component is, excuse me, let me move this properly. The x component is Vx0, that's that 5 meters per second, times the time. The z component is, the y component is 0, and the z component is Vz0 times time minus 1/2 gt squared. Okay, I'm just asserting that this vector is a solution that is motion that satisfies Newton's equations. So Newton's equation. Let's just prove it. I ask you to prove it in the notes. I will initially do this for you. So the first thing is we want to find what is. So to see if it satisfies Newton's law, we want to find what's the acceleration, and see if that is equal to my times mass, and see if that's equal to the presumed initial force. So dr dt is the is the three components of that are the derivatives of the x, y, and z component. So what's the derivative of Vx0t? Well, with respect to time, well, that should be obvious. That's just Vx0. So that leads to that one. What's the derivative of 0? Should be obvious. 0. What's the derivative of this expression with respect to time? Well, there's two parts to it. Vz0 times t is just Vz0. And 1/2 gt squared, what's the derivative? The derivative of t squared is just 2t. So the 2 cancels the 2 in the denominator, and this is just minus gt. Okay, and this will be the velocity vector. Okay, going from that to acceleration. I'm not sure what happens here. Why certain things don't scroll. But I will scroll this up. And scroll it up. Okay. And then we will do acceleration is the derivative of the velocity. Well, there's three components. The derivative of Vx0, 0, because Vx0 is just a constant. The derivative of 0, which again is 0. And the derivative of this expression here. And the derivative of that expression is two components. Well, first the derivative of Vz0, which is a constant, so that part is 0. And the derivative of minus gt, which is just minus g. Okay, so the acceleration is 0, 0, minus g. Okay, so then I say, what is mass times acceleration? Mass times acceleration is simply multiply mass by each of these components, 0, 0, minus mg. And that's the original assumed equation for the force acting on this particle. So, and so then I have shown that this solution satisfies Newton's equations. Okay, and then kind of be able to reproduce this, and then also use this solution with the presumed initial values of Vx0 and Vz0 to find what is that time at which the particle returns to the ground. So the particle has an initial upward motion, an initial motion in the x direction. At what time does the z component become equal to 0? So basically what I'm doing is I'm setting this expression right here, set that to 0. Okay, so at what time does the particle initially has an upward motion, and then at some point it returns to the ground, set that to 0 and solve. And then once I have that value of that time, how far has it traveled in the x direction in that time? So once I have the time, I put it into here to find the distance traveled in the x direction. Okay, that's it for the first part of this. I will continue the second part in another video.